Hello everyone, I am presenting my project detection and forecasting using IoT based sensor data and hybrid machine learning models. This project leverages IoT traffic data and machine learning to address congestion in modern cities. Abstract. Traffic congestion causes severe urban challenges, delays, fuel wastage, and pollution. In my work, I proceed a large IoT dataset, applied machine learning models, and achieved 92% accuracy in conjunction detection. Forecasting experiments showed that short-term predictions are reliable, enabling smart city applications. Problem statement. The main problem is that traditional traffic systems are static and fail to adapt to real-time traffic flow. My project builds an adaptive pipeline that not only detects congestion but also forecasts it in advance, helping in proactive traffic management. Research objectives. My key objectives were detect conjunction levels using IoT data, forecast short term traffic volumes, compare classical machine learning models with deep learning, build a scalable end to end pipeline suitable for smart cities. In literature review, existing studies highlights IoT modules like RFID, IR sensors, and wireless protocols. For adaptive signals, AI methods such as neural networks and predictive analytics show promise, but many lack real-world scalability. My project extends his work by combining a 2.8 million record real-time dataset with machine learning models in an end-to-end solution. Dataset description. Huawei MRC dataset, March 2020, 2.89 million records, 337K unique vehicles, 6 intersection, 44 road edges, futures, entry exit times, vehicle IDs, intersections. In future entry exit times, IDs, intersection, the data captured second by second. Traffic movements, making it rich enough for detection and forecasting. Data processing, data injection. Injection combining multiple CSVs into one dataset. Merging time field into continuous data time. Cleaning, removing duplicates and missing values. Aggregation, creating hourly windows and computing vehicle counter per intersection. Future creation, tip duration lag variables, rolling average, and cycle encoding for day and hour. Data processing, reading and combining data. In this data, we can see the data shape and the end date, end time, leaving edge, intersection, incoming edge, and start date time, end date time. In this, we can see the intersection, incoming edge. The raw dataset contains separate fields for start date and start time, end date and end time. These were merged into continuous date time objects. Start date time equals to start date plus start time. End date time equals to end date plus end time. Data processing cleaning. Data provided into multiple CSV files combined into signal data frame 2.8 million plus rows. Tools Python pandas. Here we can see the intersection, time window, vehicle count. Data processing aggregation into vehicle counts. Once the hourly window was established, detections were grouped by intersections into time window. The number of vehicles in each group formed the vehicle count metric. Here we can see the graph traffic count per hour. In the length of start date, we can take the March and 2000, 4000, 6000, 8000, 10,000, 12,000. Future engineering. In future engineering, it includes a temporal day of week, hour of day, encoded cyclically, lag futures, vehicle counts from prior hours, rolling statics, mean deviation max values to capture build-up trends. This helped models learn real traffic dynamics rather than row counts. In rolling window statics, target variables, this process of creating new predictors that capture useful pattern in the data. The raw data which counts will not provide any information. Without of these steps to provide sufficient and accurate information. Time future, lag future, rolling window statics, and target variables. Modeling approach, conjunction classification. For classification, random forecast was applied on intersection time and temporal future. It achieved 92% accuracy in distinguishing low, medium, and high conjunction. F1 scores also exceeded 90% across classes. This shows random forest provide both accuracy and stability. This classification task relied on a set of straightforward yet informative features: the encoded intersection ID, the day of the week. Conjunction classification, random forecast classifier. Random forecast classifier, XG boost classifier, evaluation, accuracy, precision, recall, F1 score. Here we can see this classification report, precision, recall, F1 score, and support. In accuracy, micro average, weight average, confusion matrix. Conjunction classification, XG boost classifier. I also tested XGBoost gradient boost model. Performance was strong, similar to RF. However, it required extensive parameter tuning. Confusion matrices showed most misclassification occurred between medium and high conjunction levels. Modeling approach, traffic flow forecasting. Random forecasting regressor was effective or short term. LSMT captured was struggled due to dataset noise. The data split was temporal 70% training, 50% validation, 50% testing to mimic real world forecasting. Evaluation metrics, classification metrics. My classification evaluation used accuracy 92%, precision, recall, balance results for each class. Evaluation metrics forecasting. For MAE 134, at T plus 1 predictions were off by 134 vehicles of RMSE revealed sensitivity to larger errors. Results showed that short-term forecasts are reliable for long-term T plus 3 prediction regret in accuracy. Results and comparison. Results are from my work: random forecast classifier best with 92% accuracy, XG boost strong but required heavy tuning, RF regressor reliable for short time forecasting, LSTV captured time pattern but less accurate due to noise. Overall, RF models were the most effective across the both tasks. In conclusion, I built end-to-end machine learning pipeline, injection, processing, future engineering, classification, and forecasting. Conjunction detection achieved 92% accuracy. Short-term forecasting achieved 88% when mapped back into conjunction categories. This pipeline is scalable for smart city developments. Future work. In future, my work can be extended by adding external data such as weather, accidents, and events, exploring advanced models, neural networks, using dynamic conjunction thresholds aligned with policy, deploying cloud edge platforms for citywide scalability. Thank you for your attention.